as a matter of fact, I received a call sometime in the middle of last week from Dr. Cecilia Marzabadi asking me if I could present a talk today, and as I couldn't say no, I said, sure, why not? And if my talk doesn't sound that appealing, please forgive me. So my talk today is going to be on the novel carbohydrate-based ligands, which have the immunomodulatory properties. She's my mentor over there. Can I have the marker? That's me over there, and this is the guy who did the biological testing of this compound. She called me up and she said it's going to be a 20-minute talk, so I have to, the 1 hour talk has to be shortened to like 20 minutes, so I had to cut short a lot of stuff. I don't have a lot on the introduction, so I'm going to jump into the synthesis part, followed by the biological testing, as well as the results and discussions, which is what's on my agenda for today. So in the introduction part, the zootynic polysaccharides, here's the picture over there, the polysaccharide PSA1, which is isolated from the capsule of the Bacteroides fragilis, has been shown to simulate both innate as well as the adaptive immune responses in mammals, and is believed to be establishing a balanced immune system, which is mediated by the T lymphocytes. So, but the earlier research work had shown that the moieties, the sugar moieties in the middle, the sugar moieties which are in the middle of both the charged moieties are of least of minimal importance. For that reason,
I hit the wrong button myself a couple of times, okay. So I think it's that top.
Okay, thank you very much. So the sugar moieties, which are in between over here, have minimal or least importance with regard to the biological properties of the molecule. For that reason, we decided to make something similar to this molecule, which has both the positive charge as well as the negative charge, but at almost at the same distance from each other. So we decided to come up with something of this kind, of the positive charge moiety followed by a negative charge moiety attached with a simple moiety, which is not a sugar, it's something like a cyclohexanediol. So that's what we decided to make, and we decided to check the potential stimuli, whether it's a potential stimuli for innate or the adaptive immune systems. And we did get some biological results on that, some positive biological results which are more appealing, and something which I'm going to talk about later on in my talk. So, by the way, we label the moieties as this is A, B, and C. I'm going to talk about the synthesis of each and every moiety in an order. So this is the synthesis of for substance of the subunit A, which is the proposed synthetic scheme, where we started with tag triacetyl D-glucan, which we did the deacetylation, followed by the selective tosylation of the primary OH. And after that, we think of preparing the ramnal, but I ran about like 15 different reactions using like 15 different reagents, and I could never get to this point. And I couldn't understand the reason why this reaction never worked, because it was published in like so many papers saying that, oh, these molecules upon detosylation and as well as the deacetylation in this case would end up giving the ramnal, but that never happened for me. But in almost all the 15 reactions, we end up seeing a new compound, which is always formed, which we didn't know what it was. And so we decided to analyze what that compound is, and that compound ended up being the 3,6-anhydride, 3,6-anhydride D-glucan moiety, and this is what the structured molecule looks like. And in this, you see the intramolecular hydrogen bonding between the molecules. So we decided to see what the reactivity of the new molecule which we came up with is like. So we ran the reactions within the presence of NIS and methanol. This is what we end up seeing. And because of steric hindrance, we couldn't see the other moiety forming. And these are the reactions. And of course, in the presence of no nucleophile, and just in the presence of the NIS, we end up seeing the formation of a dianhydride molecule. And likewise, we end up doing more reactions, this time with sodium nitrate and thiophenol in the absence of sodium nitrite and in the presence of sodium nitrite. And these are the reactions which we've observed to have, these are the molecules which we observed to have formed in these reactions. And we came up with a paper in carbohydrate research sometime last year. And if you have any questions, you can feel free to go into the paper. So coming to the sense of subunit A, I'm going to be talking hereafter only about the reactions which have worked so far, because there are innumerable reactions which we tried, which have not been, which were not successful. So if I talk about all that stuff, I need more than an hour, but I don't think I have enough time. So instead of starting with TAG, which I've talked to you about earlier, we started with glucosamine hydrochloride. In the first reaction, we tried to remove the hydrochloride part, the hydrochloride moiety from this sugar. So we treated that with sodium methoxide and methanol, resulting in formation of the glucosamine. And that upon the interaction with the thallic anhydride, followed by the acetylation, resulted in the formation of the 2-thalidomide sugar. And we tried to incorporate the thiophenol moiety, which we always incorporated at the anomeric carbon atom, but because of the steric hindrance, I think the thiophenol never added up at the anomeric carbon atom. For that reason, we end up using the smaller moiety, which is in this case like ethane thiol, and the results were amazing, and we got the desired product, and that's moiety A. And the second one is a sense of subunit A, which is subunit B, which is the more simpler one, where in case we use a cis transmixture of cyclohexanediol, 1,4-cyclohexanediol, treated that with TBDMS chloride in the presence of imidazole as well as the DMF and the formamide, and then we end up seeing the formation of the cis as well as trans isomers. And of course, we did choose the cis isomer as the compound for further studies, because that's more like a major compound which is formed in this reaction. And coming to the synthesis of subunit C, which is a little more longer compared to the earlier synthesis which I've just described. In this case, we started with the galactose sugar. It's a penta-O-acetyl galactose sugar. In this case, we treated the compound with thiophenol in the presence of BF3 ethyrate, which resulted in the formation of the thiophenol adduct, and that upon deacetylation to sodium methoxide and methanol gave this compound, the deacetylated compound, and that we decided to prevent the molecule from flipping. For that reason, we created the benzylene moiety, so that the molecule gets locked in one position and doesn't keep flipping the way it wants. So we decided, for that we treated this compound with benzaldehyde and zinc chloride, and it resulted in the formation of the benzylene moiety. And then, as there are two more OHs left behind, which we wanted to protect selectively, because we wanted to deprotect selectively when the time comes where we can add A, B, and C together. So for that reason, we decided to selectively protect one of the OH moieties, and in this case, we went to tin chemistry. We treated this compound, the benzylidine adduct, with dibutyl tin oxide in the presence of benzoyl chloride, resulting in the formation of the 2-O-benzoyl as well as the 3-O-benzoyl adducts, among which the 3-O-benzoyl is the major compound which we have chosen to go with for the next step. And the next step is quite simple. So the leftover OH, we decided to protect it with an acetyl group, which is a lot more shorter, which is a lot more smaller compared to the neighboring thiophenol as well as the benzoyl. So this reaction worked like a piece of cake, because instead of doing acetic anhydride reaction, we decided to go with acetyl chloride, and the results were amazing. I got about 98% conversion, or 98% yield in this case. And with this compound, as the moiety which I've shown you in the PSA moiety, it has the pyruvate moiety. It doesn't have the benzylene moiety. For that reason, what we did is, in the first case, we treated the compound with trifluoroacetic acid, 20% trifluoroacetic acid, and resulted in the formation of 4,6-diol sugar. And that, upon treating with methyl pyruvate in the presence of BF3 ethyrate and nitrile, resulted in the formation of the C adduct. So this slide shows the coupling of moieties A and B, which were earlier synthesized, as I mentioned to you, and A and B moieties were treated with anhydrosuccinimide in the presence of TMS triplet. In the presence of TMS triplet, which resulted in formation of this moiety, and of course, in the treatment with TBAF resulted in the decellulation and getting the desired AB couple product. But this reaction was run for 1.5 hours at minus 78 degrees Celsius, but the reaction run for about 7 hours and let the temperature go up from minus 78 degrees Celsius to 0 degrees Celsius, which ended up giving the decellular product. So it's like a one-step synthesis instead of doing the decellulation later on by using TBAF. So that's the AB adduct, which you see in this slide. And the last step is the addition of the C moiety to the already synthesized AB moiety. I did the same procedure as I used to prepare AB. I treated this compound with anisoxanimide in the presence of TMS triplet at minus 40 degrees Celsius, which resulted in formation of the PSA1 analog. And as you see, this molecule is unprotected. It is protected sugar. It's a protected moiety. We didn't go for the deproduction at this point because the amount which we had was about 100 milligrams, which we thought is a lot less, because by doing the deproduction, I'm going to end up probably with like 10-20 milligrams of the entire mass, which is not sufficient for the biological testing. So what we did is we sent the same compound to biological testing because that's what we had left behind. So the protected analog. So we looked into the innate as well as the adaptive immune responses. And first, in looking at the innate immunity, what we observed is that the protected analog was evaluated in ELISA assays for the production of the pro-inflammatory cytokines, TNF-alpha. Well, this font doesn't like me to incorporate alpha sign in there, so it's TNF-A it shows up as, but it's TNF-alpha and the interleukin-6 using the raw cells as well as the mouse peritoneal cells, the macrophages. And this is what the results look like. So for the innate immunity in the raw cells as well as the peritoneal cells, this is what the responses are like for the TNF-alpha from the supernatants, which are obtained from the cells. And so this is for the TNF-alpha, as you see here. And we did see positive responses at the end of 2 hours as well as at the end of 4 hours. And likewise, we've seen positive responses, kind of positive response. Mid response is not that amazing at the end of 24 hours, but there you see some kind of a response at the end of 48 hours for interleukin-6. Which clearly implies that the molecule, the analog 2 is showing some inflammatory activity on the cells, which is why you're producing the TNF-alpha and IL-6. So then we decided to check whether the adaptive immune system, what the response of the molecule is like for the adaptive immune system. So the molecule synthesized were also tested in spleen cells in the same mice, looking for the T cells as well as the B cell proliferation levels, as well as the levels of IF and G in the supernatants, and the polycyclonal and IgG levels in the supernatants L were measured. And what's observed is that there's no T cell or B cell responses in this test, which clearly implies that it's only the innate immune system that the molecule is responding to, and not to the adaptive immune system. So then again, going to the innate immune system, there are two different kinds of toll-like receptors, the toll-like receptors 2 as well as toll-like receptor 4 ligands, and to illustrate the bacterial toll-like receptor responsible for cytokine production, the peritoneal macrophages from TLR2 and as well as TLR4 knockout mice were dosed with the compound 2, and the TNF-alpha as well as the interleukin-6 levels were measured over time in the supernatants of the test. And this is what the results look like for TNF-alpha. At the end of 2 hours, you see this is for the wild-type mice, and this is TLR2 knockout mice, and this is for TLR4 knockout mice. At the end of, so you see almost similar response in case of wild-type as well as the TLR2, but you see a better response over here with the TLR4 knockoff mice, the ones which don't have the TLR4. Yeah, so this is after 24 hours, we see a better result, a better response of 24 hours. And as you clearly see, the one which is in 5 microgram per milliliter is that of the analog 2, which is showing a better response in comparison to the LPS, which is the control, the positive control. Of course, 0 is the negative control, which you see over here, and the LPS is the positive control. And when in comparison, the analog 2 is showing a better response in comparison to the lipopolysaccharide. Likewise, in case of interleukin-6 production, we've seen this is what the activity is like at the end of 24 hours, and this is what the activity is like at the end of 48 hours. And in both the cases, you see that the wild type as well as the TLR2 knockoff mice behaved in a similar fashion, and in the same case over here. So it's only the TLR4s in both the cases which behaved differently. And the last biological evaluation test is by the flow cytometry, the extent of the binding of analog 2 to the TLR4 receptors was illustrated by treating the peritoneal exudate cells or the PEG cells with different concentration of the compound analog 2. The cells were then pre-incubated with the compound, after which were washed, and to the washed cells were added the antibody followed by the phytoerythrin dye, which shows the flow, which tends to be fluorescent, and the number of the colored cells were observed by flow cytometry. And this is what the results look like. And this is the control with no drug on it, but the compound 2, the analog 2 is not in here, so it's just the control. And this is with 1 microgram control, 1 microgram of the drug, and here you see it's a 50.8% response. The count, the cells of the TLR4 cells is 58. Cells with TLR4 is 50.8%, and with 1 microgram per milliliter concentration of the blocking agent, which is the drug, the analog 2, there's a slight reduction in the TLR4 count, and over here with 5 microgram per milliliter concentration, you see a little more of a little less of the TLR4 count, and with 10 microgram per milliliter sample, you see almost half of exactly half of what it was with the control, which implies that it is binding to the TLR4 receptors, the drug. So this is the same. This is the same data from the earlier slide, represented in the form of a graph. This is TLR4 expressions percent. It keeps decreasing as the concentration of the drug increases in the solution. And in order to make sure that the TLR2 is not taking part in this binding, we decided to do the same reaction with TLR2, and this is the control, and this is with 10 microgram per milliliter concentration of the analog 2, and we see almost 30.8 and 33.4, which is almost the same. So it implies that the TLR2 is not taking part in the binding. And this is summary of reduction in the production of both the TNF-alpha as well as the IL-6 was observed in only the TLR4 knockout mice, suggesting that the signaling of 2 occurs through TLR4 alone and not by TLR2. Furthermore, the magnitude of TLR4, as I mentioned to you earlier, TLR4 signaling with 2 was greater than the known TLR4 agonist, which is the LPS obtained from the lipopolysaccharide obtained from E. coli cells. In conclusions, the desired retonic polysaccharide analog of PSA1 was successfully synthesized with both amino as well as the carboxylate moieties. The biological evaluation clearly denotes that the analog 2 shows immunostimulatory properties. Analog 2 was even found to stimulate the innate immune system, but not the adaptive immune system, as discussed earlier from the biological results. And an unexpected and efficient synthesis of 3,6-anhydro-D-glucan, something which I talked about earlier, paves a route to the synthesis of interesting new carbohydrate moieties. If you have any questions, I'll be delighted to answer them.
Interesting talk. I'm not sure I can understand most of it, but my question here is that your synthetic molecules, I think you're moving into the direction of molecular mimicry in terms of its pathogen-associated molecular patterns, in particular the LPS, because you're showing that it binds, well, it activates the TLR4 because of your knockout mice. Now, these synthetic peptides, the question here is, where is it binding? Is it binding directly to the receptor, or it's going through the other two molecules that activate the TLR? For example, LPS binds to the CD14 via MD2. Does this synthetic peptide bind via that direction or directly to the receptor?
From the results obtained, we do anticipate that it binds directly to the receptor, but I'm not certain.
It's not going through the CD14.
I do anticipate that, but I can find out. I can ask the guy who did the immunological test, and I can find out and get back to you on that.
Okay. And do you have any evidence that, because TLR4 could be activated by several other kinds of means rather than direct binding? And I'm just wondering whether these synthetic peptides do go through a different route. You haven't looked at that? Or?
I have not, certainly not, yeah. As I'm mostly into the synthesis part, we didn't really look into the biological activity of the molecule.
I have one more question.
Please.
If since you do these synthetic molecules, you have that capability to do a mutation. In other words, a change of the structure, a point mutation in the structure. And that could have implication in terms of binding or, I'm thinking of more like autoimmune disease or rheumatoid arthritis, where you have this macrophages-mediated type of pro-inflammatory. And maybe these peptides could be used as a synthetic therapy.
Certainly.
What do you think on that?
That's amazing. That's an amazing thought, I would say. As a matter of fact, the compound which I synthesized can be used as an adjuvant for a vaccine. But from what you're saying, you certainly can do that, because as it's binding to the TLR4 receptors, why not? I mean, I was the first one to make this compound, so there's studies on this compound have not been done yet. So people who wanted to join the group, and if they want to work on that, they can, by following the same pathway, but making some modifications and doing some SAR studies and see what the results are like.
Okay. Possibly we're a little bit late, so maybe we'll move on, but thank you again, Vikram. Appreciate that.